Everyone talks about being able to travel at the speed of light. But does anyone ask, when will our time come to be able to travel at such speeds? The universe stretches out before us in every direction, an incomprehensibly vast ocean of darkness punctuated by islands of light. Those islands, the stars we see twinkling in the night sky, are so distant that even light itself takes years, decades, centuries, or even millennia to reach us from their surfaces. And light, as far as we understand the fabric of reality, travels faster than anything else in existence. It moves at approximately 186,000 miles per second, or about 300,000 kilometers per second. At this speed, a beam of light could circle the entire Earth more than 7 times in a single second. Yet even at this mind-boggling velocity, light from our nearest neighboring star system, Alpha Centauri, takes more than 4 years to reach our eyes. This is the fundamental challenge that has captivated physicists, engineers, dreamers, and science fiction writers for generations. If we ever hope to explore the galaxy, to visit other star systems, to truly become a spacefaring civilization that ventures beyond our tiny cosmic neighborhood, we need to find a way to travel at speeds that approach, or perhaps even exceed that of light itself. But is this even possible? Will humanity ever achieve light-speed travel? Or is it destined to remain forever in the realm of imagination? Tonight, we embark on a journey through the physics of the impossible, exploring what it would truly take to travel at light speed, why our current understanding of the universe seems to forbid it, and what theoretical loopholes might exist that could one day allow us to traverse the cosmos in ways that seem like pure fantasy today. Let us begin with something that very few people consider when they think about traveling at light speed. And that is the strange phenomenon known as relativistic mass increase. According to Albert Einstein's special theory of relativity, as an object with mass accelerates closer and closer to the speed of light, something remarkable and troublesome happens. The object's mass effectively increases from the perspective of a stationary observer. This is not merely a mathematical curiosity or an abstract theoretical prediction. It has been confirmed countless times in particle accelerators around the world, where scientists routinely accelerate tiny particles to velocities exceeding 99% of the speed of light. What researchers have discovered is that as these particles approach light speed, they require increasingly enormous amounts of energy to accelerate even slightly faster. At 90% of light speed, a particle behaves as if it has about 2.3 times its rest mass. At 99%, it behaves as if it has more than 7 times its rest mass. At 99.9%, the effective mass balloons to more than 22 times the original. And as velocity creeps ever closer to that ultimate cosmic speed limit, the mass approaches infinity. This means that to accelerate even a single gram of matter to exactly the speed of light would require an infinite amount of energy. Not merely an enormous amount, not just more energy than currently exists on Earth, but literally infinite energy, which is by definition impossible to achieve. This is why physicists often say that the speed of light is not just very fast, but represents an absolute barrier that objects with mass can never cross. But here is where things become more nuanced and fascinating. While nothing with mass can travel at the speed of light, there are theoretical constructs and possibilities that might allow us to work around this limitation. One such possibility involves the hypothetical particle known as the tachyon. Tachyons are purely theoretical particles that, if they exist, would always travel faster than light. They would never slow down to light speed, just as ordinary matter can never speed up to light speed. In the mathematics that describes them, tachyons possess what is called imaginary mass, which is a concept that sounds like science fiction, but is actually a well-defined mathematical property. The fascinating aspect of tachyons is that they would experience time and causality in ways that defy our everyday intuition. For a tachyon, moving faster than light is the normal state of affairs, and slowing down to light speed would require infinite energy, just as speeding up to light speed would require infinite energy for ordinary matter. In a sense, the speed of light acts as a two-way barrier, keeping slow things slow and fast things fast, with nothing able to cross between the two realms. However, despite decades of searching, no experimental evidence for tachyons has ever been found. Most physicists believe they probably do not exist, and if they did, they would create profound paradoxes involving causality and the flow of time. Imagine sending a message via tachyons that arrives before it was sent. The philosophical and logical problems this would create have led most scientists to conclude that tachyons are likely mathematical ghosts, interesting to contemplate, but not reflective of physical reality. Another approach to achieving something like faster-than-light travel involves not moving through space quickly, but instead warping space itself. This concept, often called the Alcubierre drive or warp drive, after the physicist Miguel Alcubierre, who first described it mathematically in 1994, works on a startling principle. Instead of pushing a spacecraft through space at tremendous velocity, you would contract the space in front of the ship and expand the space behind it, creating a wave of distorted spacetime that carries the vessel along. Inside this bubble of warped space, the spacecraft would actually be stationary, relative to its immediate surroundings. It would not be violating special relativity, because locally, it would not be moving at all. The bubble itself, however, could theoretically travel across the cosmos at any speed, including speeds far exceeding that of light. The ship would be surfing on a wave of space-time, arriving at distant stars not by traveling quickly through space, but by bringing distant points of space closer together. When Alcubierre first published this idea, it caused considerable excitement in both scientific and popular circles. Here was a theoretical framework, grounded in the mathematics of general relativity, that seemed to allow for faster-than-light travel without violating the fundamental laws of physics. However, as scientists examined the proposal more closely, serious problems emerged. The most significant obstacle involves the type of matter required to create the warp bubble. According to the calculations, generating the necessary curvature in space-time would require something called exotic matter, specifically matter with negative energy density. In our everyday experience, all matter and energy have positive density. An apple, a rock, a beam of sunlight, all possess positive energy. Negative energy density is something that has been demonstrated to exist in extremely limited circumstances in quantum physics. But generating the quantities needed for a warp drive appears to be far beyond anything we could conceivably achieve. Initial calculations suggested that the amount of exotic matter required would exceed the mass energy of the entire observable universe. Later refinements by physicists have reduced this estimate dramatically, with some suggesting that a warp bubble could theoretically be created with the mass energy equivalent of several hundred kilograms of matter. While this is still an enormous amount of energy, it brings the concept at least marginally closer to the realm of possibility. Yet even with these refinements, we have no idea how to create exotic matter with negative energy density in any usable form. The quantum effects that produce tiny amounts of negative energy in laboratory conditions, such as the Casimir effect, are so minuscule that scaling them up to spaceship-sized applications seems like asking how many drops of water it would take to fill the Pacific Ocean, except worse, because we do not even know if the ocean can be filled with this particular type of water at all. There are also concerns about what would happen at the boundary of a warp bubble. Some calculations suggest that as the bubble accelerates to high velocities, it would sweep up particles and radiation from space, concentrating them at the front of the bubble into an increasingly powerful beam. When the bubble slows down or collapses at its destination, this accumulated energy might be released in a devastating blast that could sterilize any planet the travelers were hoping to visit. Arriving at a new world only to destroy it would somewhat defeat the purpose of interstellar exploration. Additionally, some physicists have argued that there might be no way for occupants inside a warp bubble to control its operation. They would be causally disconnected from the bubble's edge, meaning they could not send signals to steer, accelerate, or stop the device. The bubble would have to be programmed in advance, like a train on a fixed track, with no brakes and no conductor. Let us turn now to another approach that has captured the imagination of scientists and science fiction authors alike: the concept of traversable wormholes. A wormhole, in the language of physics, is a hypothetical tunnel through spacetime that connects two distant points. Instead of traveling the long way around through normal space, a spacecraft entering one mouth of a wormhole could emerge almost instantaneously from the other mouth. Even if that other mouth were located in a completely different galaxy, the mathematics of general relativity allows for the existence of wormholes. They emerge naturally from the equations as solutions to Einstein's field equations, the fundamental mathematical description of how matter and energy curve space-time. However, the wormholes that appear in these solutions are typically unstable, collapsing faster than anything could pass through them, or they require exotic matter with negative energy density to remain open, bringing us back to the same problem that plagues the Alcubierre drive. Theoretical physicist Kip Thorne, who later won the Nobel Prize for his work on gravitational wave detection, explored the possibility of traversable wormholes in detail during the 1980s. Working with his graduate students, Thorne showed that if exotic matter could be obtained in sufficient quantities and arranged in the right configuration, it might be possible to prop open a wormhole and allow travelers to pass through. The requirements are daunting. The wormhole would need to remain stable for the duration of the journey, which might be mere seconds from the traveler's perspective, but could involve enormous stresses on the structure of space-time itself. The exotic matter would need to line the throat of the wormhole, holding it open against the powerful gravitational forces trying to collapse it. And the travelers would need some way to navigate through this tunnel without being torn apart by tidal forces or radiation. Some scientists have proposed that naturally occurring wormholes might exist, perhaps created in the violent early moments of the universe, or in the extreme gravitational environments around black holes. If such wormholes could be found and somehow stabilized, they might provide ready-made shortcuts through the cosmos. However, we have no observational evidence that such structures exist, and the theoretical reasons for believing they might exist remain highly speculative. Perhaps the most sobering aspect of wormhole travel is what it implies about causality and the nature of time itself. Under certain conditions, a wormhole could theoretically be transformed into a time machine, allowing travelers not just to cross vast distances instantly, but to arrive in the past. This possibility has led many physicists to suspect that some as yet unknown law of physics might prohibit traversable wormholes entirely. Stephen Hawking famously proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel, and therefore to prevent the construction of traversable wormholes or any other faster-than-light transport mechanism. Let us consider now a different approach to interstellar travel, one that does not violate the speed of light limit, but instead embraces the strange consequences of traveling close to it. This is the phenomenon of time dilation, and it offers a genuinely achievable if still extraordinarily difficult, path to the stars. According to special relativity, time passes more slowly for objects moving at high velocities. This is not an illusion or a trick of perception. It is a fundamental aspect of how the universe works, confirmed by countless experiments. Atomic clocks flown on high-speed aircraft have been shown to run slightly slower than identical clocks left on the ground. Particles created in cosmic ray collisions survive longer than their stationary counterparts because they experience time differently at their relativistic speeds. For a spacecraft traveling at 90% of the speed of light, time on board would pass at about 44% of the rate experienced by people remaining on Earth. At 99% of light speed, time dilation becomes even more extreme, with shipboard time passing at only about 14% of the Earth rate. And at 99.9%, the ratio drops to roughly 4.5%. What this means in practical terms is quite remarkable. A spacecraft traveling at 99.9% of light speed could reach Alpha Centauri, 4.37 light-years away, in about 4.4 years, as measured by clocks on Earth. But for the crew on board, only about 2.4 months would have passed. They would arrive at their destination having aged less than a tenth, as much as their colleagues back home. At higher velocities, this effect becomes even more pronounced. At 99.99% of light speed, the crew might experience only a few days of travel time, while decades pass on Earth. At 99.999%, the disparity grows to centuries or millennia of Earth time for days of shipboard time. In principle, by traveling fast enough, astronauts could traverse the entire observable universe within a human lifetime of subjective experience. Though billions of years would pass for everyone else, this offers a genuine, physics-compliant method of reaching the stars within a human lifetime. The catch, of course, is that the travelers would be one-way pioneers, arriving at their destination to find that everyone they knew back on Earth had long since died. Civilizations had risen and fallen, and the world they left behind no longer existed in any recognizable form. It is interstellar travel, not as a round trip, but as a permanent emigration across time, as well as space. The engineering challenges of approaching even a fraction of light speed are immense. Let us consider what would be required to accelerate a spacecraft to just 10% of light speed, a velocity that would still take more than 40 years to reach Alpha Centauri. At this speed, the kinetic energy of the spacecraft would be enormous. A 100-ton vessel traveling at 10% of light speed would carry kinetic energy equivalent to about 10,000 megatons of explosive force, roughly 200 times the yield of all nuclear weapons ever detonated in the history of humanity. Generating and controlling this much energy would require technologies far beyond our current capabilities. Chemical rockets, the most powerful propulsion systems we have deployed for interstellar probes, produce exhaust velocities of only a few kilometers per second, millions of times too slow for relativistic travel. Nuclear thermal rockets might achieve exhaust velocities perhaps 10 times higher, still hopelessly inadequate. Even the most advanced theoretical propulsion concepts we can envision, such as nuclear pulse propulsion or antimatter engines, face enormous challenges. Nuclear pulse propulsion, most famously studied in the Project Orion designs of the 1950s and 60s, would use the explosive force of nuclear bombs detonated behind a spacecraft to accelerate it. Calculations suggested that such a system might achieve velocities of 3 to 5% of light speed, enough to reach nearby stars within a human lifetime, though not within a comfortable margin. However, the engineering challenges of building a spacecraft that could survive the repeated nuclear explosions, carrying thousands or tens of thousands of bombs, and protecting its crew from radiation would be formidable. the political and environmental obstacles to launching such a vessel from Earth would be equally daunting. Antimatter propulsion offers potentially higher performance, but faces even more severe practical difficulties. When matter and antimatter come into contact, they annihilate completely, converting their entire combined mass into energy, according to Einstein's famous equation relating energy and mass. This makes antimatter the most energy-dense fuel conceivable, carrying roughly 1 billion times more energy per kilogram than chemical fuels, and thousands of times more than nuclear fission. A spacecraft carrying antimatter fuel could theoretically achieve velocities approaching a significant fraction of light speed. Some calculations suggest that a well-designed antimatter rocket could reach speeds of 40 to 70% of light speed, bringing Alpha Centauri within reach in less than 10 years of Earth time, and perhaps just a few years of ship time. However, we currently produce antimatter only in trace amounts, a few nanograms per year, from particle accelerators around the world. Manufacturing the kilograms or tons of antimatter needed for an interstellar mission would require energy inputs billions of times greater than our current global production, and we have no idea how to store such quantities safely. Antimatter annihilates on contact with ordinary matter, so containment requires electromagnetic fields that can suspend the antimatter in a vacuum without ever allowing it to touch the walls of its container. Scaling this up from the few atoms we can currently trap to the quantities needed for spaceflight is a challenge of almost inconceivable difficulty. Let us now explore some of the more exotic propulsion concepts that theoretical physicists have proposed, ideas that exist at the very edge of scientific speculation and might offer pathways to even higher velocities. One intriguing possibility involves harnessing the energy of black holes. Black holes are not merely cosmic vacuum cleaners that suck in everything around them. They can also be tremendously efficient engines for converting matter into energy. When matter falls toward a black hole, but does not quite cross the event horizon, it can be accelerated to extreme velocities and heated to billions of degrees, radiating away much of its mass as pure energy before either escaping back into space or finally falling into the black hole. In the accretion disks around black holes, this process converts roughly 10 to 40% of infalling matter's mass into radiated energy, far more efficient than nuclear fusion, which converts less than 1%. If we could somehow create and control a miniature black hole, or position ourselves near a natural one, we might tap into this tremendous energy source for propulsion. Theoretical physicist Freeman Dyson and others have speculated about what he called a Dyson sphere, a hypothetical megastructure completely surrounding a star to capture all of its energy output. A civilization capable of building such a structure might redirect that captured energy into laser beams or other propulsion systems, accelerating spacecraft to significant fractions of light speed. The energy output of our sun alone, if captured completely, would be sufficient to accelerate millions of tons of spacecraft to relativistic velocities every year. A more modest version of this concept, sometimes called a Dyson swarm, might be achievable by a civilization perhaps only a few centuries more advanced than our own. Instead of a solid shell around the sun, a swarm of billions of solar collectors could capture a significant fraction of solar output and direct it toward spacecraft equipped with enormous light sails. The Breakthrough Starshot initiative, announced in 2016 with funding from physicist Yuri Milner, proposed using ground-based lasers to accelerate gram-scale probes to 20% of light speed, enough to reach Alpha Centauri in about 20 years. While the initial concept focuses on tiny probes carrying only cameras and communication equipment, the same principle could theoretically be scaled up to larger vessels, given sufficient energy. The concept of a Bussard ramjet, proposed by physicist Robert Bussard in 1960, offers another theoretical approach. Instead of carrying all its fuel from Earth, a Bussard ramjet would scoop up hydrogen atoms from the thin gas that fills interstellar space, fusing them for propulsion. Since the fuel supply would be essentially infinite, such a vessel could theoretically accelerate continuously for as long as desired, reaching velocities arbitrarily close to light speed. Unfortunately, closer analysis has revealed severe problems with the Bussard ramjet concept. The interstellar medium contains only about 1 hydrogen atom per cubic centimeter on average, requiring an enormous scoop to collect significant quantities. The drag created by this scoop might exceed the thrust generated by the fusion engine, actually slowing the spacecraft rather than accelerating it. And the magnetic fields needed to funnel hydrogen into the collector would have to be light years wide for the concept to work as originally envisioned. Variations on the ramjet concept continue to be explored. Some proposals suggest using the scooped hydrogen not for fusion, but as reaction mass, expelled at high velocity, using energy from an onboard power source. Others propose augmenting the ramjet with laser beams from home bases, providing additional acceleration during the early stages of the journey when the spacecraft is still within range of the laser stations. None of these variations has yielded a practical design, but the fundamental idea of harvesting fuel from space remains tantalizing. Let us consider now what the experience of traveling at near light velocities might actually be like for the occupants of such a spacecraft. The effects would be profoundly strange, altering the very appearance of the universe around them. As a spacecraft accelerates toward light speed, the stars ahead would appear to shift toward the blue end of the spectrum, their light compressed to shorter wavelengths by the Doppler effect. Stars behind would shift toward the red, their light stretched out. At very high velocities, visible stars would crowd together toward the front of the ship, concentrated into a brilliant disk of compressed light, while the rear sky grew increasingly dark. Radiation from all directions, including the cosmic microwave background that normally fills the universe as a faint whisper of primordial heat, would be concentrated and blue-shifted into dangerous beams of high-energy particles. A ship traveling at 99% of light speed would experience the cosmic background radiation as intense X-rays bombarding its forward shields. At even higher velocities, this radiation would shift into the gamma-ray spectrum, requiring shielding of tremendous thickness to protect the crew. The ship would also encounter dust and gas particles that populate interstellar space. At relativistic velocities, even individual hydrogen atoms would strike the hull with the energy of high-speed projectiles. A grain of interstellar dust, perhaps a millionth of a gram in mass, would hit with the force of an artillery shell. The forward sections of the spacecraft would need armor capable of withstanding continuous bombardment by these cosmic bullets, or perhaps a powerful magnetic field to deflect charged particles, or laser systems to vaporize larger debris before impact. Inside the ship, passengers would experience time passing normally. They would not feel compressed or stretched by relativistic effects. Their heartbeats, their conversations, their meals would all proceed at the ordinary pace of human life. Only when comparing their clocks with those left behind on Earth would the time dilation become apparent, revealing that years or decades had passed for the outside universe, while mere weeks or months elapsed on board. If the ship accelerated continuously at one Earth gravity, which would provide comfortable artificial gravity for the passengers, it could reach 99% of light speed in about 1 year of ship time. Maintaining this acceleration for another year would bring the ship even closer to light speed, into the regime of 99.9% and beyond. The passengers would feel nothing unusual during this process, just a comfortable one-gravity push, pressing them gently into their seats or onto the floor, indistinguishable from standing on Earth's surface. The possibilities this opens for exploration are remarkable. With continuous one-gravity acceleration to the midpoint of a journey, followed by continuous one-gravity deceleration to the destination, almost any location in the observable universe could theoretically be reached within a human lifetime of subjective ship time. The center of our galaxy, 26,000 light-years away, could be reached in about 20 years of ship time. The Andromeda galaxy, 2.5 million light-years distant, would take only about 28 years. Even the edge of the observable universe, 46 billion light-years away in terms of current distance, would be reachable in about 45 years of ship time, though billions of years would pass on Earth. Of course, these calculations assume that we can solve the energy problem, that we can build engines capable of sustaining one-gravity acceleration for years or decades, and that we can protect passengers from the hazards of the journey. No known technology comes close to meeting these requirements. But the physics itself does not prohibit such journeys, only our current engineering capabilities. Let us explore now what recent developments in physics might suggest about the feasibility of light speed or faster-than-light travel. In the past few decades, several discoveries have revealed that the universe is stranger than even Einstein imagined, and some of these discoveries might eventually open doors we cannot currently see. The discovery of dark energy in the late 1990s showed that the expansion of the universe is accelerating. Space itself is stretching at an ever-increasing rate, driven by a mysterious energy that permeates the vacuum. In the distant future, galaxies that are currently visible will be carried away from us faster than light, disappearing beyond our cosmic horizon forever. This means that space can expand faster than light, even if nothing can move through space faster than light. The distinction is subtle but crucial, and it is exactly the principle that underlies the Alcubierre warp drive concept. Quantum entanglement, the phenomenon Einstein called spooky action at a distance, involves correlations between particles that seem to be transmitted instantaneously, regardless of the distance separating them. When two particles are entangled and one is measured, the other instantly takes on a correlated state, even if it is on the opposite side of the universe. However, extensive theoretical and experimental work has shown that despite appearances, no information can be transmitted faster than light using entanglement. The correlations are real, but they cannot be used for communication because the results appear random until the two observers compare notes, which requires ordinary light-speed limited communication. Still, entanglement hints that the universe contains deeper connections than our everyday intuition suggests. Some physicists have speculated that these connections might eventually be understood in ways that allow for faster-than-light effects. The ER equals EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests that entangled particles might be connected by microscopic wormholes. If true, this would unify two seemingly different phenomena, quantum entanglement and general relativistic wormholes, into a single underlying reality. Whether this could ever be exploited for faster-than-light communication or travel remains highly speculative. String theory and its extension, M theory, suggest that our universe might contain additional spatial dimensions beyond the three we perceive. These extra dimensions, if they exist, are thought to be either incredibly tiny, curled up below the scale of atoms, or somehow hidden from our direct perception. Some theorists have proposed that gravity might leak into these extra dimensions, which could explain why gravity is so much weaker than the other fundamental forces. If we could somehow access these extra dimensions, we might find shortcuts through space-time that are invisible from our three-dimensional perspective. The concept of brains in string theory suggests that our entire visible universe might be a three-dimensional membrane floating in a higher dimensional space called the bulk. Other brains might exist nearby in this bulk space, tantalizingly close in the extra dimensions, even if infinitely far away in the dimensions we can perceive. Some cosmological models suggest that the Big Bang itself might have been caused by a collision between brains. If we could somehow travel through the bulk rather than along our brain, we might bypass the speed of light limit that applies to motion within our familiar dimensions. These ideas remain highly speculative, far removed from any experimental verification or practical application. But they illustrate that our current understanding of physics, as comprehensive as it seems, might be only a small piece of a much larger puzzle. New physics could emerge from experiments at particle colliders, from observations of extreme cosmic events, or from mathematical breakthroughs that reveal connections we cannot currently see. Any such discovery might transform our understanding of what is possible for interstellar travel. Let us turn now to consider the practical steps that might lead toward faster propulsion systems in the coming decades and centuries, moving from current technology toward the ambitious concepts we have discussed. The first rung on this ladder involves improving our current rocket technology. Chemical rockets have powered all of human spaceflight so far, from the first satellites to the Apollo moon landings to the Mars rovers. But chemical propulsion is fundamentally limited by the energy content of chemical bonds, which provides exhaust velocities of only a few kilometers per second. Even the most energetic chemical reactions cannot push this limit much higher. Ion propulsion, already used on some spacecraft, offers significantly higher exhaust velocities by electrically accelerating ions to tens of kilometers per second. The Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, used ion propulsion to achieve velocity changes that would have been impossible with chemical rockets given its mass budget. However, ion thrusters produce very low thrust, taking months or years to achieve the velocity changes that chemical rockets accomplish in minutes. Nuclear thermal propulsion, where a nuclear reactor heats propellant to extreme temperatures before expelling it, could roughly double the efficiency of chemical rockets. NASA and private companies have recently revived interest in nuclear thermal propulsion for missions to Mars, where the reduced travel time could significantly lower radiation exposure for astronauts. Plans are underway to test nuclear thermal engines within the next decade, potentially opening the door to faster transit times throughout the inner solar system. Nuclear pulse propulsion, despite its dramatic nature, remains technically feasible with current technology. Project Orion in the 1960s produced detailed designs for spacecraft propelled by successive nuclear explosions, demonstrating through theoretical calculations and actual explosive tests that the concept could work. Political and environmental concerns halted the project, and the Partial Nuclear Test Ban Treaty of 1963 made atmospheric nuclear detonations illegal. However, if launched from space rather than from Earth's surface, nuclear pulse propulsion might become viable as our space infrastructure develops. Solar sails and laser sails offer propellantless propulsion, avoiding the tyranny of the rocket equation that limits all exhaust-based systems. The pressure of sunlight is real, but extremely gentle, and current solar sail designs accelerate slowly. However, given enough time, a solar sail can achieve velocities far beyond what chemical rockets can manage. The Planetary Society's light sail missions have demonstrated the technology in Earth orbit, and Japanese space agency JAXA successfully flew the Ikaros solar sail to Venus in 2010. Laser sails could achieve much higher accelerations by using powerful laser beams rather than sunlight. The breakthrough Starshot concept, mentioned earlier, proposes using a 100-gigawatt laser array to accelerate gram-scale probes to 20% of light speed. While still in the early study phase, this concept has received serious attention and funding, with technical analyses suggesting it might be achievable within a few decades if sufficient resources were devoted to it. Fusion propulsion remains the most promising medium-term option for high-performance interstellar propulsion. If we can develop controlled fusion reactors, the same technology could, in principle, power spacecraft with exhaust velocities of hundreds or thousands of kilometers per second, approaching 1% of light speed. Various fusion propulsion concepts have been studied, including magnetic confinement systems similar to tokamaks, inertial confinement using lasers to compress fuel pellets, and more exotic approaches like muon-catalyzed fusion. The challenge with fusion propulsion is that we have not yet achieved practical fusion power generation on Earth, despite decades of research. The plasma in a fusion reactor must be heated to temperatures exceeding 100 million degrees and confined long enough for the fusion reactions to produce more energy than was required to initiate them. Recent advances, including the National Ignition Facility's achievement of fusion ignition in 2022, suggest that this goal may finally be within reach. If fusion power becomes practical for terrestrial electricity generation, the technology will inevitably be adapted for spacecraft propulsion. Antimatter propulsion, as discussed earlier, offers the highest theoretical performance, but faces daunting production and storage challenges. Current antimatter production yields only nanograms per year at tremendous cost, far too little for any practical application. However, several proposed methods might dramatically increase antimatter production if developed. These include harvesting antimatter from the natural environment, where it is created by cosmic ray collisions with the atmosphere, or using powerful lasers to create matter-antimatter pairs directly from concentrated light. Even storing antimatter safely remains an unsolved problem. The Penning traps used to contain small amounts of antimatter in laboratories today are extraordinarily delicate, holding only a few thousand antiprotons in magnetic suspension. Scaling this up to the milligrams, grams, or kilograms needed for various propulsion concepts would require entirely new approaches, perhaps involving solid antimatter frozen into a lattice of normal matter, or contained within the intense magnetic fields of ultra-cold superfluids. As we consider these technological stepping stones, it becomes clear that the path to light-speed travel, if it exists at all, will be long and incremental. Each advancement opens possibilities for the next, building toward capabilities that seem impossible today, but might become routine in future centuries. The history of technology offers some perspective here. In 1800, the fastest any human had ever traveled was perhaps 40 miles per hour, on horseback or in a sailing ship with favorable winds. By 1900, steam locomotives routinely exceeded 100 miles per hour. By 1969, Apollo astronauts traveled at 25,000 miles per hour, escaping Earth's gravity on their way to the Moon. The Parker Solar Probe, launched in 2018, has achieved speeds exceeding 400,000 miles per hour, making it the fastest object ever built by humans. This progression from 40 miles per hour to 400,000 miles per hour occurred over just 2 centuries. Yet even the Parker Solar Probe's tremendous velocity is only about 1/18,000th of light speed. To reach the nearest star in a human lifetime would require another leap of similar magnitude, from 400,000 miles per hour to tens of millions of miles per hour. Whether we can make such a leap, and how long it might take, remains deeply uncertain. Some analysts have attempted to project when various propulsion capabilities might become available based on historical trends in technology development. These projections are highly speculative, subject to the impossibility of predicting future discoveries and the tendency of technological progress to accelerate unexpectedly in some areas while stalling in others. If fusion propulsion becomes practical within the next 50 years, spacecraft capable of reaching perhaps 1% of light speed might follow within another century. At this speed, a mission to Alpha Centauri would take about 450 years, far too long for a crewed voyage, but potentially feasible for robotic probes or generation ships carrying communities of colonists whose descendants would arrive at the destination. Antimatter propulsion, if the production and storage challenges can be overcome, might push spacecraft to 10% or even higher fractions of light speed. At 10% of light speed, Alpha Centauri becomes reachable in about 45 years, still longer than a typical career, but within the working lifetime of scientists who might launch the mission and live to see results. Such a mission might become feasible within 2 to 3 centuries if antimatter production follows a trajectory similar to other technologies that have developed from laboratory curiosities to industrial processes. Laser sail propulsion for small probes might achieve 20% of light speed within decades if projects like Breakthrough Starshot succeed. Scaling this up to larger payloads and eventually to human passengers would require laser arrays of almost unimaginable power, potentially taking centuries to develop. But the fundamental physics is already understood, and the primary challenges are economic and engineering, rather than requiring new scientific breakthroughs. More exotic concepts like the Alcubierre warp drive or traversable wormholes are impossible to schedule on any timeline because we do not know if they are even physically possible. If negative energy density in macroscopic quantities can be produced, these technologies might become feasible within a few centuries of that discovery. If negative energy density is fundamentally impossible in the required forms, these concepts will remain forever in the realm of speculation. Let us pause now to consider the implications of interstellar travel for human civilization, should it ever become possible. The distances involved are so vast, and the time scale so long, that interstellar travel would transform not just technology but culture, society, and perhaps human nature itself. Even at 99% of light speed, with time dilation reducing ship time to about 14% of Earth time, a round trip to a star 50 light-years away would take more than a century of Earth time. The travelers would return to find their grandchildren elderly or dead, their culture transformed beyond recognition, their world a foreign country. This is not travel as we understand it, but permanent exile, a choice to leave behind everything familiar in exchange for the experience of visiting another star. For colonies established at distant stars, communication with Earth would involve similar delays. A message sent from a planet orbiting a star 100 light-years away would take 100 years to reach Earth, and another 100 years for any response to return. Conversations would be impossible. Colonists would share news and culture in slow packets, more like correspondence between generations than communication between individuals. Over time, such colonies might evolve their own cultures, technologies, and even biological characteristics, diverging from Earth humanity as surely as species diverge when separated by geographic barriers. The possibility of time dilation adds another dimension of complexity. If different colonies have access to different propulsion technologies or make different choices about travel speeds, their experiences of time would diverge dramatically. A ship traveling at 50% of light speed experiences time at about 87% of the rate of a stationary observer. A ship at 90% of light speed experiences time at about 44% of the Earth rate. And a ship at 99.9% experiences time at only about 4.5% of the Earth rate. Consider a scenario where Earth sends colonists to 2 different stars, one nearby and one far away. The nearby colony reached in 20 years of ship time at 50% of light speed, would arrive only 40 years after Earth's clocks record their departure. The distant colony, reached in 20 years of ship time at 99% of light speed, would arrive 143 years after their departure by Earth's calendar. When these colonies eventually contact each other, the nearby colony might have had 100 years to develop, while the distant colony had only 57 years since their arrival. The biological generations would be mismatched, with the nearby colonists being the great-great-grandchildren of the original settlers, while the distant colonists might still include some members of the original crew. This temporal scrambling would make governance, trade, and coordination across interstellar distances extraordinarily challenging. Different colonies might adopt different time standards, different calendars, different units of measurement. A civilization spanning multiple star systems might fragment into isolated communities that share a common origin but develop independently, reconnecting only occasionally when ships or messages traverse the vast distances between them. Some science fiction authors have explored these themes in depth, imagining civilizations where the time costs of travel determine political boundaries more than physical distance. In such settings, empires might persist across thousands of light years if relativistic travel keeps subjective time short, while nearby systems might be effectively isolated if slow travel means generations pass during each journey. The experience of interstellar travelers themselves would be profoundly disorienting. Imagine leaving Earth at age 30, spending 3 subjective years on a journey to a star 50 light-years away, and arriving at age 33 to find that 70 years have passed on Earth. Everyone you knew before departing is dead or elderly. The music, fashion, politics, and technology of your childhood are ancient history to the people who greet you. You are a time traveler, but you can only travel forward, never back. For colonists or explorers who intend to return home, this effect makes round trips effectively impossible for any journey beyond a few light years. Either you commit to a one-way trip, building a new life at your destination, or you accept that everyone and everything you loved on Earth will be gone by the time you return. Some travelers might embrace this, seeing the opportunity to witness the future as a privilege worth any sacrifice. Others might find the prospect too isolating to contemplate. This psychological dimension of interstellar travel receives less attention than the physical challenges, but may prove equally important. Humans evolved in small communities where separation from family and tribe meant danger and likely death. Our psychology is built for connection across distances of miles, not light years. How would individuals and societies adapt to the radical separations that interstellar travel would impose? What new forms of relationship, commitment, and community might emerge? Some researchers have begun to study these questions seriously, drawing on analogies with historical long-distance voyages, remote communities, and isolated environments like Antarctic research stations. The experiences of early ocean explorers, who sometimes left home for years, knowing they might never return, offer partial parallels. But even the longest sea voyages of the age of exploration lasted only a few years and covered distances that light crosses in milliseconds. The psychological challenges of interstellar travel would be qualitatively different, requiring new approaches to mental health, social organization, and personal meaning. Generation ships, vessels designed to travel for centuries, with communities of inhabitants whose descendants would eventually arrive at the destination, raise additional questions. How would you design a society intended to persist for dozens of generations in a completely closed environment? How would you maintain the skills, knowledge, and motivation needed to operate the ship and establish a colony at arrival. What happens if the inhabitants decide partway through the journey that they no longer want to colonize a distant star, preferring to live out their lives on the ship? These questions have been explored in both scientific studies and science fiction, with proposals ranging from strict social hierarchies maintained across generations to egalitarian communities making decisions by consensus, from extensive automation that reduces human responsibilities to deliberate preservation of agrarian lifestyles that keep inhabitants connected to the work of survival. No consensus has emerged because we have no experience with such communities and cannot test our assumptions except through thought experiments and simulation. As we continue to rest and reflect, let us turn to the question of whether the speed of light represents an absolute limit or merely the boundary of our current understanding. Throughout the history of science, barriers that seemed insurmountable have often yielded to new knowledge, and light speed might be no different. In the 18th century, chemists believed in phlogiston, a substance they thought was released when materials burned. The phlogiston theory explained many observations, but could not account for the fact that some materials gained weight when burned, rather than losing it. Eventually, the discovery of oxygen and the development of modern chemistry swept away phlogiston entirely, replacing it with a more accurate understanding of combustion. In the late 19th century, physicists struggled to explain the pattern of light emitted by hot objects, a problem known as black body radiation. Classical physics predicted that hot objects should emit infinite amounts of high-frequency radiation. Obviously incorrect, since we are not constantly bathed in deadly ultraviolet light. Max Planck's introduction of energy quantization, the idea that energy comes in discrete packets rather than continuous amounts, resolved this paradox and launched the quantum revolution. The speed of light limit arises from special relativity, which has been confirmed by countless experiments and has never failed a test. But special relativity describes the structure of space and time. It does not tell us the final truth about reality. Theories that go beyond special relativity, incorporating gravity through general relativity or quantum effects through quantum field theory, reveal that spacetime is more dynamic and strange than the flat, fixed arena that special relativity describes. Perhaps some future theory will reveal that the speed of light limit, while absolutely valid within the framework of special relativity, does not apply to phenomena we have not yet discovered. Just as quantum mechanics showed that the apparently solid, deterministic world of classical physics was underlain by probabilistic waves, a future theory might show that the apparently rigid speed limit of light is underlain by deeper structures that permit faster-than-light phenomena under certain conditions. Some theoretical hints point in this direction. The information paradox in black hole physics suggests that information might be transmitted in ways that seem to violate locality, the principle that effects only propagate at light speed or slower. The holographic principle, arising from string theory and black hole thermodynamics, suggests that the information content of a region of space is proportional to its surface area rather than its volume, implying that our three-dimensional experience might emerge from a more fundamental two-dimensional reality. If space-time itself is emergent, arising from more fundamental quantum information processes, then the speed of light limit might be a property of the emergent structure rather than an absolute feature of underlying reality. These speculations are far from proven, and many physicists regard them skeptically. But they illustrate that our current theories, despite their remarkable success, might not be the final word. The history of science counsels humility about the permanence of any theoretical framework, even one as well established as relativity. At the same time, we must be cautious about assuming that future physics will conveniently provide whatever technologies we desire. The fact that we want faster-than-light travel does not mean that physics will eventually allow it. Many barriers in nature are absolute. Entropy always increases, energy is always conserved, and so on. The speed of light might belong to this category of truly fundamental limits, rather than the category of barriers that yield to technological progress. Some physicists have argued that the speed of light limit is deeply connected to the logical structure of causality and might be necessary for any coherent universe to exist. If effects could precede their causes, as faster-than-light travel seems to permit under certain conditions, then the basic framework of physical law might break down entirely. The universe might protect itself against such paradoxes by simply not allowing faster-than-light travel under any circumstances. The Fermi paradox, the question of why we have not detected any evidence of alien civilizations despite the vast age and size of the universe, might be related to the speed of light limit. If advanced civilizations arise frequently in our galaxy, but are forever confined to the slow crawl of sublight travel, they might remain isolated from one another, never meeting even over billions of years. Alternatively, if faster-than-light travel is possible, and even one civilization has achieved it, we might expect to see evidence of their presence throughout the galaxy, which we do not. The apparent emptiness of the cosmos might be telling us something about the ultimate limits of travel through space. Let us consider now some of the most recent research and developments in propulsion physics, bringing our exploration closer to the present day. In the field of electromagnetic propulsion, researchers have continued to investigate devices that seem to produce thrust without expelling propellant, violating the fundamental principle of momentum conservation. The most famous of these devices, the M drive, received significant attention in the 2010s when NASA's EagleWorks laboratory reported measuring tiny amounts of thrust from a microwave cavity that should not have produced any force at all. However, subsequent investigations have failed to confirm these results. More careful experiments have shown that the apparent thrust was likely caused by measurement errors, thermal effects, or electromagnetic interference with the test equipment. As of the early 2020s, no credible evidence supports the existence of propellantless electromagnetic propulsion. The physics community generally regards claims of such devices with deep skepticism, though research continues at low levels. In theoretical physics, work continues on understanding the nature of spacetime and whether it might permit faster-than-light phenomena. The Alcubierre metric and its variants remain active areas of research, with physicists exploring whether the extreme energy requirements might be reduced through more sophisticated geometries or alternative approaches to generating the necessary spacetime curvature. In 2021, physicist Eric Lentz proposed a class of soliton solutions to the Einstein equations that might create warp bubbles without requiring negative energy. These hyperfast solitons, if physically realizable, could travel faster than light, using only positive energy densities. However, the energy requirements, while not requiring exotic matter, remain astronomically large, roughly equivalent to hundreds of times the mass of Jupiter converted entirely to energy. Whether practical methods exist to generate and control such energies remains unknown. Other researchers have explored the quantum vacuum as a potential source of propulsion energy. The quantum vacuum is not empty, but seethes with virtual particles constantly popping into and out of existence. The Casimir effect, where closely spaced metal plates are pushed together by vacuum fluctuations, demonstrates that this quantum energy is real and can produce measurable forces. Some proposals suggest that advanced manipulation of vacuum fluctuations might provide a source of propulsion energy, though no concrete mechanism for extracting useful quantities of energy from the vacuum has been demonstrated. Research into wormholes has also continued, with physicists exploring which types of wormhole configurations might be stable and traversable. Work by physicists including Kip Thorne, Matt Visser, and others has mapped out the requirements for different wormhole geometries, generally finding that some form of exotic matter or negative energy is required. However, the amounts needed vary greatly depending on the wormhole structure, and some configurations require less exotic matter than others. A particularly interesting development involves the relationship between quantum entanglement and spacetime geometry. The ER equals EPR conjecture, mentioned earlier, suggests that entangled particles are connected by microscopic wormholes. If this is true, the distinction between quantum mechanics and general relativity becomes blurred, and understanding one might provide insights into the other. Some physicists speculate that this connection might eventually reveal ways to engineer macroscopic wormholes using quantum effects, though this remains highly speculative. In 2020 and 2021, experiments at particle accelerators and laboratories around the world continued to test the predictions of special and general relativity to ever greater precision. No violations of relativity have been found, strengthening confidence in the theory, while simultaneously confirming the challenges faced by faster-than-light proposals. At the same time, new gravitational wave observations have provided unprecedented tests of general relativity in extreme conditions, again finding excellent agreement with Einstein's predictions. The detection of gravitational waves themselves has opened new possibilities for understanding spacetime. Gravitational waves are ripples in the fabric of space itself, traveling at exactly the speed of light. The observation of gravitational waves from colliding black holes and neutron stars has confirmed predictions of general relativity and demonstrated that spacetime is a dynamic medium that can be distorted and set vibrating. Whether this dynamic nature might someday be harnessed for propulsion remains to be seen. As we continue our journey through this topic, let us consider the broader context of interstellar exploration and what motivates humanity to reach for the stars, despite the enormous challenges involved. Throughout history, humans have been driven to explore the unknown, to cross oceans, to climb mountains, to map new territories. This drive seems deeply embedded in our nature, perhaps a legacy of our ancestors' migration out of Africa and across the globe. Every habitable landmass on Earth was eventually colonized by humans, from tropical islands to frozen tundras, from dense jungles to arid deserts. Space represents the ultimate frontier, the final ocean to cross. The Moon and Mars are already within our reach, using existing technology, though establishing permanent settlements will require decades of effort and enormous investment. The outer planets and their moons present greater challenges, but are not fundamentally beyond our capabilities. But interstellar space is different, representing a barrier of distance that dwarfs all previous frontiers. Some argue that we should focus our attention on problems closer to home, rather than dreaming of distant stars. Earth faces urgent challenges including climate change, resource depletion, and social inequality that might absorb all our energies for centuries to come. Why devote effort to interstellar travel when we have not yet learned to live sustainably on our own planet? Others respond that exploration and aspiration toward grand goals bring out the best in human civilization, inspiring cooperation, innovation, and long-term thinking. The Apollo program, whatever its Cold War motivations, produced technological spin-offs, educated a generation of engineers and scientists, and demonstrated that humanity could accomplish remarkable feats when united in common purpose. A serious interstellar program might have similar effects, galvanizing efforts that produce benefits far beyond space exploration itself. There is also the practical argument for spreading humanity beyond Earth as a hedge against extinction risks. Our species currently exists on a single planet, vulnerable to asteroid impacts, supervolcanic eruptions, pandemics, or our own technological mishaps. Establishing self-sustaining colonies on other worlds would provide insurance against such catastrophes, ensuring that human civilization and consciousness could survive even if Earth becomes uninhabitable. For this insurance to be truly effective, colonies would need to be far enough from Earth to avoid shared catastrophes. A colony on Mars might be destroyed by the same asteroid that destroys Earth, or might remain dependent on Earth for critical supplies that could not be provided after a global disaster. Only truly interstellar colonies, thousands of light years away, would provide genuine insurance against existential risks. The search for extraterrestrial life provides another motivation for interstellar exploration. The discovery of life beyond Earth, whether microbial or intelligent, would be one of the most significant events in human history, transforming our understanding of our place in the universe. While telescopes and space probes can detect some signs of life from a distance, detailed investigation of alien biospheres would likely require visiting them directly. If intelligent life exists elsewhere in our galaxy, contact with such beings could provide knowledge and perspectives accumulated over millions of years, potentially answering questions that humans might never solve independently. Alternatively, if we find the galaxy empty of intelligence, despite billions of years of evolutionary opportunity, that discovery would carry its own profound implications about the rarity of consciousness and our responsibility as perhaps the only minds in the cosmos. These considerations give interstellar travel a significance beyond mere exploration or adventure. The stars represent our future as a species, the arena where human destiny will play out over timescales that dwarf recorded history. Whether we reach them through slow ships that take millennia, relativistic vessels that compress time for their passengers, or technologies yet undreamed that might someday allow true faster-than-light travel, the journey to the stars will define what we become. Let us now return to our central question. When will we be able to travel at light speed? Based on everything we have discussed, we can offer some tentative conclusions. True light-speed travel for objects with mass appears to be physically impossible according to our current understanding of physics. The infinite energy requirement imposed by relativistic mass increase is not a mere engineering challenge, but a fundamental feature of spacetime structure. No foreseeable technology can circumvent this limit within the framework of special relativity. Faster-than-light travel through warp drives, wormholes, or other means remains theoretically conceivable, but requires exotic matter or conditions that we have no idea how to produce. Progress in fundamental physics might someday reveal pathways to these technologies, or might conclusively demonstrate that they are impossible. We cannot currently predict which outcome will occur or when. Near light-speed travel using relativistic effects and time dilation is physically possible and might become achievable within several centuries if technological progress continues. Such travel would allow reaching distant stars within a human lifetime of subjective experience, though centuries or millennia would pass for those left behind. The engineering challenges are immense, but do not require new physics. Only dramatic improvements in energy production, propulsion systems, and spacecraft construction, more modest velocities, perhaps a few percent of light speed, might be achievable within a century or two using advanced nuclear propulsion, antimatter engines, or beamed energy systems. Such velocities would enable interstellar probes to reach nearby stars within decades. and might support generation ships that could carry colonists to new worlds over the course of several centuries. The timeline for any of these developments is highly uncertain. Technological progress is difficult to predict even a few decades ahead, let alone centuries. Revolutionary discoveries could accelerate timelines dramatically, while unexpected obstacles could delay progress indefinitely. The social, political, and economic factors that determine which research programs receive funding and support are even harder to forecast than the technical feasibility of particular approaches. What we can say with confidence is that the dream of interstellar travel has motivated serious scientific research for more than a century and continues to inspire new generations of physicists, engineers, and dreamers. The questions we ask about the limits of speed are also questions about the nature of space, time, and reality itself. Pursuing them advances our fundamental understanding, even if the practical applications remain distant. In the coming decades, we will likely see continued development of propulsion technologies for the inner solar system, with nuclear thermal engines and advanced ion drives enabling faster missions to Mars and beyond. We will see continued investment in fusion research, which might eventually lead to the high-performance engines needed for interstellar precursor missions. We will see ever more sophisticated space telescopes studying nearby exoplanets in detail, identifying targets for future exploration. Whether the generation that hears this is the one that launches the first interstellar probe, or whether that milestone lies centuries in the future, the effort will continue. The stars call to us across the void, their light carrying an invitation to explore that we cannot ignore. The universe is vast beyond comprehension, and our place in it is tiny beyond measure. Yet we have managed, in just a few thousand years of civilization, to understand the basic laws that govern reality, to send our machines beyond the planets, to glimpse the beginning of time itself. Whatever the ultimate limits of travel through space may prove to be, we have already accomplished more than our distant ancestors could have imagined, and we will continue to reach further than we can currently conceive. As your thoughts drift towards sleep, consider the immensity of the cosmos and the audacity of our aspirations. Somewhere out there, perhaps around a star whose light is only now reaching Earth after a journey of millions of years, there might be worlds of unimaginable wonder waiting to be discovered. We may never walk on those worlds ourselves, but our descendants might, or their descendants after them. The dream of the stars is not just ours. It belongs to all the generations that will follow, stretching forward into a future we can barely imagine. The night sky has inspired wonder since the first humans looked up and asked what the lights in the darkness might be. We know now that they are suns, some like our own, and some vastly different, many surrounded by planets, some perhaps harboring life, or even minds that wonder about us in turn. We know that the distances between them are immense, so vast that even light takes years to cross them. And we know that reaching them will require either physics we do not yet understand, or technologies we cannot yet build. But we also know that every barrier humanity has faced before has eventually yielded to ingenuity, persistence, and time. The oceans that seemed uncrossable are now traversed by millions of people every year. The moon that seemed forever unreachable has felt the footsteps of a dozen human explorers. The very structure of atoms, once thought to be indivisible, has been probed and harnessed for purposes both destructive and beneficial. There is no guarantee that the speed of light will yield as other barriers have, but there is also no proof that it cannot. In the gap between certainty and impossibility lies the space where discovery happens, where the questions we cannot answer today become the knowledge of tomorrow. Let your thoughts settle now into the quiet contemplation of these vast questions. The universe continues its ancient dance, stars burning through their nuclear fuel, galaxies wheeling through the void, light crossing the emptiness at its unchanging speed. Somewhere in this cosmos, perhaps in your lifetime, or perhaps many generations hence, the first human artifact will depart our solar system, bound for another star. And somewhere in the more distant future, perhaps human beings themselves will make that journey, carrying with them all our hopes, dreams, and curiosity into the galaxy that awaits. The questions we have explored tonight do not have final answers, only the tentative conclusions of our current understanding and the open possibilities of future discovery. This is the nature of science, always provisional, always open to revision in light of new evidence. The speed of light might prove to be an absolute barrier, or it might prove to be merely a local speed limit that more advanced physics can circumvent. We will not know until we try, until we push the boundaries of knowledge and technology as far as they can go. For now, the stars remain distant, their light traveling for years before it reaches our eyes. But in that light is encoded information about distant worlds, about the elements that compose them, about the conditions that prevail in places we have never visited. Every photon that reaches us is a message from across the cosmos, an invitation to learn, to understand, to explore. And explore we shall, in our telescopes and space probes and theoretical calculations, in our dreams and our determination. The question is not whether we will reach for the stars, but only how far our reach will extend and how long the reaching will take. The universe is patient, having existed for nearly 14 billion years before we arrived. It will wait for us, its wonders preserved by the vast distances that currently keep us apart. In the meantime, there is much to discover closer to home, in the planets of our own solar system, in the depths of our own world, in the mysteries of our own minds. Each discovery builds on those that came before. Each question answered opening new questions to ask. This is the endless frontier of knowledge, always expanding, always revealing new horizons beyond the ones we have just crossed. The journey to light speed, if it is ever completed, will be the work of many generations, each contributing what it can before passing the torch to those who follow. We are part of that chain, our current efforts laying groundwork for futures we cannot see. This is how civilizations progress, through the accumulated efforts of countless individuals who may never see the fruits of their labor, but who labor nonetheless, driven by curiosity and hope. As the night deepens around you and sleep approaches, let these thoughts accompany you into rest. The cosmos continues its ancient processes, whether we observe them or not. But something is different because we are here to wonder about them. Consciousness has emerged in this vast universe, and with it, the desire to understand, to explore, to reach beyond our origins towards something greater. Whether we ever achieve light-speed travel, or must content ourselves with slower journeys through the cosmic sea, the dream itself has value. It lifts our eyes from the immediate concerns of daily life toward the vast sweep of time and space in which we are embedded. It reminds us that we are part of something much larger than ourselves, a universe of beauty and mystery that invites our exploration. The stars will still be there when you wake, their light having traveled a tiny bit farther while you slept. The questions about speed and travel and the nature of spacetime will still await answers that only future generations may provide. But for now, rest is appropriate. The body and mind needing renewal for whatever challenges and wonders tomorrow may bring. Let the rhythm of your breathing slow. Let the tension in your muscles ease. Let the thoughts about light speed and relativistic travel fade into the background as sleep approaches. The universe will continue its ancient dance while you rest, and when you return to wakefulness, it will still be there, vast and mysterious, and waiting to be understood. The light from distant stars continues its journey across the void, some of it having left its source before humans existed, before our planet formed, before our sun ignited. That light carries the story of cosmic history, written in wavelengths we are only now learning to read. And someday, perhaps, we will carry our own light to those distant places, human presence reaching beyond our tiny corner of the cosmos into the greater universe that has always surrounded us. For now, though, sleep beckons, offering rest and renewal. The questions about interstellar travel will wait, patient as the stars themselves, for the minds of tomorrow to pursue them. Each generation adds what it can to humanity's collective understanding, and each generation sleeps at night as you sleep now, gathering strength for the work that remains. The journey is long, whether measured in miles or light years, in hours or centuries. But every journey consists of single steps, and every step brings us closer to wherever we are going. Tonight, the step is rest. Tomorrow, the journey continues. That wondering continues in you, in this moment, as you consider the possibility of light-speed travel and all that it would mean. It continues in laboratories and observatories around the world, where scientists probe the nature of space-time and the limits of propulsion. It continues in the imaginations of children who dream of visiting other planets, other stars, other galaxies. The dream of reaching the stars is one of humanity's oldest and most persistent aspirations. It has motivated some of our greatest achievements and inspired countless works of art, literature, and philosophy. Whether or not we ever achieve true light-speed travel, the dream itself has value, pointing us towards something greater than our everyday concerns, and reminding us of the vast context in which our lives unfold. As you drift towards sleep, let that dream accompany you, a gentle companion in the darkness. The stars shine on, indifferent to our presence, but beautiful nonetheless. The light they emit will continue traveling across the void long after we are gone, carrying information about distant suns to distant places where other beings might someday observe it. We are participants in a cosmic story that began long before we existed and will continue long after we are forgotten. Our chapter is small but significant, for it is in our generation that many crucial questions will be asked, and some will be answered. What we discover about the nature of space-time, about the possibilities and limits of travel, about the existence of life elsewhere in the cosmos, will shape the trajectory of human civilization for millennia to come. But that is work for waking hours. Now sleep calls, offering the rest that makes all our endeavors possible. The questions will wait, patient as they have always been, for the minds of tomorrow to address them. Let your thoughts settle. Let your body relax. Let the vast contemplations of interstellar travel recede into the gentle background of approaching sleep. The universe continues its ancient processes, stars burning, planets orbiting, light traveling, and somewhere in the midst of all this cosmic activity, you rest, gathering energy for whatever comes next. The night deepens, the stars wheel overhead in their eternal patterns, and the questions about light-speed travel remain open, awaiting the answers that only time and effort can provide. Someday, perhaps, those answers will come, and human beings will stand on the surface of a world orbiting a distant star, looking back toward our sun, now just another point of light in an alien sky. Until then, we dream, we wonder, we rest, and we continue the work of understanding that defines our species. The journey to the stars is not just a physical journey, but a journey of the mind, a quest for knowledge that enriches our lives, whether or not we ever set foot on distant worlds. Sleep now, surrounded by the vastness of the cosmos and the warmth of human aspiration. The questions will wait, the stars will endure, and the dream of reaching them will continue to inspire generation after generation, until someday, somehow, in ways we cannot now imagine, the impossible becomes possible, and the distant becomes near. The adventure of human existence continues, carrying us forward into whatever futures await. For tonight, rest is the next step in that adventure, a necessary pause before the journey resumes. Let go of waking thoughts. Let the contemplation of light speed and relativistic effects fade into the peace of approaching sleep. The cosmos awaits, patient and eternal, ready to reveal its secrets to those who seek them. Someday, those secrets might include methods of travel that seem like magic to us today. Or they might confirm that some barriers are truly absolute, that the speed of light defines a limit we can approach but never cross. Either way, the asking of questions has its own value, the journey of understanding its own rewards. We are privileged to live in an age when these questions can be asked with scientific precision, when the dream of interstellar travel can be subjected to rigorous analysis, when the resources exist to at least begin the work of reaching beyond our solar system. Future generations will build on what we achieve, just as we have built on the achievements of those who came before. This is how progress happens, through accumulated effort across time, through the patient work of countless individuals who contribute what they can to the great project of understanding. For tonight, your contribution is rest, allowing the body and mind to renew themselves for whatever challenges and opportunities tomorrow may bring. The questions about light speed will still be there when you wake, the stars still shining, the cosmos still expanding, the mystery still beckoning. Let sleep come now, a natural conclusion to this long contemplation of space and time and travel. The universe continues its dance, and you are part of it. A conscious point of awareness embedded in the vast cosmic fabric, wondering about the nature of that fabric and the possibilities it might contain. Sweet dreams await, perhaps of journeys through the stars, of worlds we have never seen, of futures we can barely imagine. Let those dreams carry you through the night, gentle reminders of the aspirations that make us human. The question of when we will travel at light speed remains open, awaiting the discoveries and inventions of generations yet to come. But the dream of reaching the stars is already real, already inspiring, already pointing us towards something greater than ourselves. Rest now, dreamer of the stars. The cosmos will wait.